by Zirui Yanhua Yuling Wang, Kangkang Zixuan Liang Tat-Seng Chua. The paper is entitled Information-Controllable Graph Contrastive Learning for Recommendations. We have on the stage Daryl Chang, maybe.
Hi, everyone. Since the authors for this paper cannot attend the conference on site, so I am the proxy presenter for this paper titled Information-Controllable Graph Contrastive Learning for Recommendation. In this presentation, I will share their research in 3 parts. First, let's discuss the background behind their study. Traditional recommendation models like collaborative filtering often suffer from data sparsity. These models require a large amount of user-item interaction data to generate accurate recommendations. However, in many real-world scenarios, user behavior data is sparse and new users or items further exacerbate this issue. This is where graph constructive learning comes into play. In GCL-based recommendation, the main idea is to create multiple augmented views of the user-item interaction graph and train the model to align these views to a constructive learning goal. Typically, this process involves 3 steps. First is data augmentation. The interaction data is augmented by techniques like edge dropout or load masking or generating subgraphs. This augmented graph provides slightly different perspective of the same underlying data. And the second is constructive learning. Using these augmented views, the GCL method learns to maximize the similarity between the positive pairs, that is the same user or same item across different views, and minimizing the similarity between negative pairs, that is different users or items. And the third step is the representation learning. Through the constructive learning, constructive loss function, the GCL learns robust representations for users and items, and using them to generate recommendations for the users. However, most existing graph constructive learning methods fail to effectively control the amount of shared information between constructive views. That is to say, they will lead to the problem of augmented representation collapse. Let's see the picture. This results in representation that only is similar, making it difficult to capture the unique characteristics of different data views. In this picture, it compares the similarity distribution of the typical graph constructive learning method, SGL, and the same GCL. In the picture, we can see that they tend to produce highly similar representations for the positive users, and resulting they are losing critical distinguish features needed for effective recommendations. So, the main reason behind the augmented representations collapse in existing GCL methods lies in the nature of their constructive loss function. The loss function is the info NCE loss, and it is designed to maximize the similarity between positive pairs while minimize the similarity between negative pairs. However, their training, the loss function tends to push the representations of positive pairs closer together until they are similarly approaches 1, while this helps in aligning the different views and learning the common characteristics, but it can cause the learned representations to lose their diversity as the views become nearly identical for the same users or items. This phenomenon is known as representation collapse. Such a collapse is problematic because it leads to the loss of critical task-relevant information for make accurate recommendations for each user. For example, in the user-item interaction graphs, unique aspects of a user's preference should be learned in different views of the augmented graph, but this may be overlooked in existing methods if all positive pairs have nearly identical representations. Next, let's go to our proposed method, IGCL. We proposed the Information-Controllable Graph Contrastive Learning framework, that is IGCL. Let's take a closer look at how the model operates. IGCL consists of 3 key modules. The first is Collaborative Signal Enhanced Augmentation, CSEA module. This module aims to generate augmented representations that retain high-order collaborative signals, which is crucial for make recommendations. Instead of relying on traditional rule-based perturbations, this module directly incorporates collaborative signals into the augmented views. This is done using a graph-based encoder like multi-layer GCL, which captures intricate user-item interaction patterns, and it issues that the augmented representations contain not only the necessary variations for constructive learning, but also rich information that is relevant to the recommendation task. And the second module is the Information-Controllable Constructive Learning. A unique aspect of IGCL is the focus on controlling the degree of similarity shared among different views. This is done by introducing a reconstruction loss to maintain an optimal level of information shared between the main and augmented views. This loss function is designed to issue that the representation of positive pairs do not become overly similar, thus preserving diversity. At the same time, the IGCL module introduces an augmentation encoder that learns to optimize the shared representation characteristics dynamically, making the constructive process more adapted to the recommendation task. And the third part of this framework is the user preference prediction part. This part using the augmented and the original views to generate the representations for users and items, and use the inner product to produce the preference scores for users to make accurate recommendations. And they first analyzed the time complexity across various components, including the vital part in existing graph constructive learning methods, including perturbation, graph encoding, and loss function. The primary difference in time complexity comes from the perturbation process and the number of graph encodings needed for each augmented graph. For instance, SGL and SIM-GCL generate multiple augmented views, which leads to a higher time complexity due to repeated graph perturbation and graph encoding. However, in IGCL's design, it integrates the reconstructive loss for controlling shared information, which incurs some, while it incurs some computational cost, but it only applies one augmented graph to generate a single perturbation view, so it will remain more efficient than methods requiring making multiple augmentations. Finally, I will introduce the experiment's results. Here, we evaluate IGCL alongside various state-of-the-art baselines on 3 real-world datasets, and in these experimental results, we can see IGCL has shown performance improvements in all metrics on all datasets. Compared to the SOTA baselines, including some strong constructive learning approaches, by injecting task-related information and controlling the shared information between different augmentation graphs, IGCL ensures that the shared information between views contains as much task-relevant information as possible, but maintaining an appropriate magnitude, enabling IGCL to surpass existing solutions in current constructive learning approaches, that is SGL, SIM-GCL, and AutoCF. The augmentations strategies typically overlooked the balance of shared information. Consequently, this oversight may result in the acquisition of an excessive amount of shared noise at the expense of vital task-specific information. And then we calculated the similarity of all user positive pair representations learned by SGL, SIM-GCL, and IGCL on 3 datasets. It is evident that across all datasets, SGL consistently exhibits the highest peak value of similarity. More specifically, it adds 3 times that of the similarity than that of SIM-GCL and 4 times that of SGL on the T-more dataset. Additionally, the location of the peak value of SGL is closer to 1, especially on Yelp and the T-more dataset, indicating a significant representation collapse phenomenon. Beyond the peak values, observing the range of similarity distribution, SGL and SIM-GCL are more concentrated than IGCL on all 3 datasets. They are primarily distributed in the range of 0.98 to 1, whereas IGCL has a broader distribution than the baseline constructive learning methods. This is beneficial for the constructive loss to focus on positive pairs with varying degrees of similarity. Overall, IGCL effectively mitigates the issues of augmented representation collapse by controlling the shared information between positive pairs through reconstruction loss. Compared to SGL and SIM-GCL, they exhibit weaker collapse phenomena. So as SIM-GCL exhibits weaker collapse phenomenon. That is the reasons for its relatively superior performance. So finally, we use the TSNE to show the distribution of the learned representations. The uniformity of the representation distribution can reflect the ability of the model to preserve the user's unique preferences for recommendation. We randomly sampling 2,000 users from T-more and Amazon datasets to show the learned representations. On T-more, it can be observed that light GCN results in more clusters compared to the GCL-based methods, indicating that light GCN is unable to effectively distinguish the unique preference of users. Within these clusters, the users shared some common preference, but it's not good for make accurate representations. In the GCL-based methods, SIM-GCL and IGCL both show a uniform distribution, but importantly, compared to the baseline methods, IGCL have a more dispersed distribution in the center. On Amazon, the distribution of IGCL has is noticeably more dispersed and closer to a cycle. This suggests that there are certain distance maintained between users in IGCL, which effectively preserve users' Unicode preference. Okay, that is the end of the presentation. Since I'm not the author for this paper, so there is no question and answer part.
Thank you, thank you. Unfortunately, we have no time for questions, but we can continue, of course, offline with